Are you describing an LLM can actually provide multiple outputs, iterate on those outputs before it even presents you with the
Yes,
final output?
100%. 100%.
I didn't even consider that. That is so cool. Groq makes the fastest AI chips out there. They're called LPUs. And today we're going to talk about how they work. I was fortunate enough to interview two of their incredible engineers, Andrew and Igor, and they are both hardware and software engineers who know exactly how Groq is able to achieve 500, 600, even 700 tokens per second inference speed. And I'm going to interview them, and we talk about everything from manufacturing to the differences between NVIDIA and Groq chips to some of the incredible benefits that you get from having insane inference speeds, which even surprised me and I didn't think about. So make sure you stick around to the end because what they told me absolutely blew my mind in terms of what you can do with that kind of speed. Thanks to Groq for setting this up and sponsoring this video. Let's get into the interview now. All right. We have Andrew and Igor from the Groq team, two engineers, and I'm super excited to talk to them today. We're going to learn all about the hardware side of things and learn how Groq ended up where it is today at the fastest inference speed that I've ever seen. So we have a lot to get into, but first, Andrew, I would love to just hear a little bit about you, how you joined Groq, and a little bit about your career.
Yeah, definitely. I started in this space really through my graduate studies, University of Toronto, great school for computer architecture, machine learning, did a PhD, really kind of this really esoteric area like compilers and FPGAs, and then spent, more than a decade just building compilers, I would say, at various semiconductor companies, starting out with just like, C++ compilers. But then that evolved, particularly roughly like 2016-ish, when like AlexNet and all these things started taking off. Kind of like my team kind of evolved into a machine learning compiler team. And that's roughly when I got wind of Groq. Groq started 2016. I knew a bunch of folks within the company, more on the business side. I actually didn't know the founder, Jonathan, at the time. But a lot of my colleagues ended up at Groq. Because there's a lot of sort of similarities to what I was doing and the business that I was in and what Groq was doing, really accelerating and reinventing silicon. So that's really how I ended up here. I just kind of got pulled in from a mutual network, and then I've been here roughly 4 years, and it's been incredibly satisfying and exciting to really see the company mature. Yeah, and we're going to talk about what it's like today because Groq is everywhere. But Igor, I want to hear the same thing from you. How did you get into hardware? What was your career? And then how did you end up finding and joining Groq?
Yeah. So I think we've started at the same school. So I went to U of T as well, University of Toronto. And then my first serious job was at IBM Microelectronics. This is in the Vermont area. I kind of moved through the ranks there. That ASIC organization that I was working with was an organization that was building custom chips. At that point, we were doing custom chips for a lot of networking applications. And then those networking chips ended up looking very much like AI chips as we started moving. Lots of memory, lots of SerDes and things like that. I became the CTO of that organization as it moved to Global Foundries. And in fact, that's where I met Jonathan. So when I met Jonathan in 2016, he was just starting Groq. So when I met him, it was about 7 engineers on the Groq side in a tiny little office. We had to steal chairs from across the room to actually have our first meeting. And that led to the first chip. This is the chip that we're discussing today. This is the LPU. And this is the chip that we're kind of running on these workloads. So after that, I kind of transitioned through Marvell. I was the CTO of the ASIC business unit at Marvell. Then I moved to Google. So I was leading the custom silicon effort for the TPU. So this is the AI accelerator from Google. So I was working on optimizing the physical design for that accelerator. And at that point, Jonathan pinged me again, and he was saying, hey, we're doing this next big thing. It's time for you to join. So I've kind of stayed in touch with Jonathan throughout that. So it was kind of an easy jump. I think there's some really cool architectural features of this design that are kind of unique, and they're really like a silicon architect's dream. So I couldn't say no to that.
Yeah.
So
Okay.
I started back with Groq 2 years ago. So I've been with Groq for 2 years now.
Awesome. Awesome. Yeah. And there's definitely something unique about the hardware. And I am a novice, to say the least, on all hardware topics. So I'm going to be trying to ask intelligent questions, but I want to learn more about what is so special about the hardware. But before we get there, let's start with what traditional GPUs, traditional hardware to run inference looks like. So how do you describe it? Like what from the highest level, what does it look like?
So I think visually, what you see on the left is the graphics processor unit. So this is the GPU. And what you see is really a state-of-art silicon, right? You see the largest silicon interposer, the largest die that you can manufacture that's the size of a reticle, effectively over 800 millimeters, 6 HBMs. These are 3D stack DRAM memories that are really high bandwidth, or at least as high bandwidth as you can if they're off chip. And it's implemented, the core is implemented in 4 nanometer, which is really kind of pushing the limits of what Moore's Law is giving you in return, right? So really complex design.
And what does the nanometer actually mean? What does that give you when it's smaller?
Yeah, so nanometers have become more of a marketing thing right now, but they're effectively supposed to be the minimum feature size that you are implementing on that chip. So think of transistors, they're so tiny now, you can actually fit tens of thousands of them in a single red blood cell. That's how tiny they are. And that 4 nanometer is kind of like the smallest feature of that transistor. At least that's what it's supposed to mean. They've kind of lost a little bit of touch of the actual physical size, but roughly that would be the information that you get with that 4 nanometer.
Okay. And Igor, you mentioned a couple other terminologies. Maybe you can just very briefly describe what those mean and kind of how they contribute to the performance of a traditional chip.
Yeah, sounds good. So if you look at inside, I don't know if you can see my mouse, but if you can see here, this is the core die. So this is the compute die that's implemented in the latest and greatest kind of process node. And that compute die is effectively doing a lot of the heavy compute work. Next to it, you see these boxes. Those are high bandwidth memories. So those are effectively multiple dies like these stacked one on top of another in implementing DRAM, which is a form of a memory, dynamic random access memory. And what they are there to do is to store a lot of information, a lot more information that you can store on the chip. The downside is that memory is significantly slower than what you can actually implement on chip, right? And the bandwidth to one of these memories could be hundreds of times slower than the bandwidth that you get on the chip. But they're kind of like a really good storage unit that you have along the side of the chip.
So if I'm buying a gaming GPU and it describes it as 16 gigabytes, is that what you're describing right now?
Maybe if it's a really, really high-end graphics card, typically those would be a lower bandwidth memory, so GDDR or something like that. But yes, you could have HBMs that could be providing some of that data. Yeah, so that would be the DRAM. The number that you specify, that is a DRAM capacity.
Got it. Okay, thank you.
Yeah. So that's the GPU. It's kind of pushing the limits on biggest reticle, biggest silicon interposer, most number of HBMs that you can implement at that time when H100 was kind of the most advanced kind of piece of silicon, a piece of SoC. On the right, you see the LPU. So this is the chip that we implemented first at Groq. So this is in 14 nanometer. So 14 nanometer means it's about 3 nodes older than the 4 nanometer that the GPU is using. So just to give you the nodes, from 14, you would have moved to 10 nanometer, 7 nanometer, 5 or 4 nanometer. So technically, you're getting significantly less transistors than you would have in 4 nanometer. So technically, you're supposed to be significantly slower or less amount of work with a 14 nanometer chip than you could with a 4 nanometer chip. because the devices are bigger and you can put less of those devices in the similar actual silicon space. Does that make sense?
Yeah, it does make sense. And I'm sure there was good reasoning behind the decision to use larger or kind of couple generations older nanometers. But I would love to hear why and then how did you decide on these trade-offs?
Yeah. So part of the decision was made because this chip was manufactured many years ago, basically like 3 or 4 years ago. So at that point, 14 nanometer was near the most advanced node that you can use. And that was part of the decision. The other part of the decision, we wanted to have silicon that's manufactured right here in the US. So to kind of maintain a supply chain that's in the US, this silicon was actually manufactured in Malta, New York, in Global Foundries. It was packaged in Bromont, Canada. And then, as Andrew is on the call here, Andrew's team actually is doing all the compiling. In other words, moving these algorithms into the silicon to kind of do specific, to implement a specific workload. So those were the two major decisions that led to a 14 nanometer silicon decision.
Understood. So to clarify, the Groq chip as we know it today was actually designed a few years ago.
That's correct. Yeah.
Okay. And it seems like, and we'll get to this, but something has occurred in the last few months where people are realizing just how powerful it is. Now, I know you guys already knew it, but let's come back to that.
Yep.
Like what was it about the state of the market, the state of inference that kind of made everybody look at this and say, oh, this is actually super valuable. Let's start switching to Groq. But in the meantime, I see non-deterministic for the traditional GPU and deterministic for the Groq chip. I would love maybe you could just give a brief definition of what deterministic means, and then also like how does that actually affect the chip's performance?
So maybe we actually have like a little animation here that kind of takes you through that. So what we mean by non-deterministic is that when a task is supposed to complete in the compute portion of the chip, it might complete very quickly if the data that processor is working on is nearby in a thing called cache, like a local cache. Mm-hmm. But it also might take a lot longer time if it needs to access that data from an HBM. So you can see this Gaussian that shows every time you contact the HBM, you might be able to get the data that you're working on in as few as 300 nanoseconds. That's 300 billionths of a second. Or it might take you a microsecond to get that data. So what that means is that you never quite know how quickly you'll be able to get the job done. So it's non-deterministic, basically.
Got it. And how does that affect the chip's performance? And was that one of the key decisions that led the LPU to be so unique and to perform at the rate that it's able to with its inference speed?
Yeah. So I'll cover the hardware piece, but then I'll pass on the benefits of determinism to Andrew, because on the software side, right?
Awesome.
On the hardware side, on the left side, what you see is many cores that are making up this chip. So these are think of small processing units that are all executing on their own time. And then they need to combine all these results to kind of get the global job done. But if you have one core that's waiting for the HBM to provide data, then all the cores are kind of waiting for that data to be completed. So you're kind of slow as the slowest core in the group. And not just that, because AI is now not only a single chip problem, but it's a multi-chip problem. And the more non-determinism you have in the system, the harder it is to get the job done in a very expeditious way.
Yeah. So, as more on I'm more on the software side, if I'm doing a job asynchronously and everything else is waiting on that job, then everything else is as slow as that job.
It is. And then that brings complication on the software side. So maybe Andrew can kind of touch on that piece, the complication. And then we'll switch to the LPU so we can explain to you how we improve this problem or eliminate it on the LPU side.
Your intuition is spot on, Matthew. Like, if you don't know how long something's going to take, you just have to be excessively conservative. And that's effectively what you're seeing with like multi-core CPU, graphics cards. Effectively, the compilation problem is conservative, and that's why it's so hard to compile to these devices. You know, I mean, I think it's an open secret that, like, you know, the big tech companies, they really don't have automated compilers anymore. They are using armies of people to hand tune things, to actually map these ML workloads onto the silicon.
Can you elaborate on what that means exactly? Like, when I hear they have armies of actual human beings doing this, that blows my mind. Can you dive into that a little bit?
No, it's true. It sounds a little bit counterintuitive because you think about like all the automation that we have, all the compilers that we have. Like, isn't this a solved problem? It's not. This is the hardest problem in computer science. We've effectively, I mean, the industry in general has effectively given up on making the holy grail automated vectorizing compiler that gets peak performance. So perfect example, Intel, they have the math kernel library, right? MKL. That's actually written for the most part by hand. I mean, they have templates, they have some level of automation in that, but for the most part, they're sort of templated, handwritten libraries by these extremely smart, very talented, mathematicians and computer scientists. And they are the best in the world that can do this. But they have hundreds or thousands of these engineers to do this. And the compiler is just really invoking these library calls under the hood. And that's how you're eking out all the performance. You see this in all industries, like in fintech, all the folks in fintech who want the peak performance, they've kind of, kicked the compiler to the side and just started writing these things by hand. If you take a look at what they're doing under the hood for all of these finance applications. So extremely tough problem. The strategy that the big tech companies are taking makes sense, right? They have the capital to do this. We could not do that, right? We're a small startup, we don't have infinite amount of money. We had to do something different. So that's really the core of why A, our chip looks so different, and B, how we're getting this amazing performance out of it. In fact, Jonathan, who started the company, I think the first 6 months, he only thought about the software. He literally did not think about the underlying hardware that would run this. He thought about it more like a decomposition and graph problem of, okay, given a ML workload, here's the general structure. How do you actually decompose a problem into its primitive form? And then from that, he devised a hardware substrate to execute those operations. So he kind of went backwards. Like, he started with the problem and went down, finally ending up to the silicon. I think to the point, like, he tells this story, I don't know how true it is, but like, he banned whiteboards in the company because everyone kept on writing block diagrams of hardware blocks. And he's like, no, stop thinking about the hardware. Let's just understand how we compile this thing in an automated way, because we cannot afford to hire 1,000 engineers to write kernels.
So the traditional workflow is the hardware engineers come up with a new design, something that they believe to be cutting edge on the hardware side. Then they essentially pass it off to a team that really had very little to no input on the hardware design, and then they are tasked with building the kernel. Is that correct?
Yeah. And that still happens quite a bit. You've heard the keywords now about software, hardware, co-design, right? And I think Jonathan was doing this in 2016, because if you look at the whole system, we're kind of talking about the chip right now, but it really have a vertical optimization across the stack, all the way, we joke around, from sand to cloud, sand being silicon, all the way to our cloud. So like Andrew's team works very closely with my team. They're embedded in our hardware meetings, and my team is embedded in Andrew's team. So we actually make decisions that are really optimized across the stack. And that's been kind of the go-to right from the get-go.
Yeah, I guess that's one of the benefits when you're coming to a problem completely fresh with, trying to really see it through a different lens, start from the ground up. You get to make certain decisions that I guess maybe other larger incumbents just took for granted.
Yeah. there's a beauty to start with a whiteboard and you have unlimited capabilities there. So I think it is I think that's how Jonathan has approached this problem. And I think it's yielded like a really a lot of benefits, not just on the hardware side, but as we move to the kind of the next slide here and kind of look at how Groq is kind of working through the hardware problem. So on the right, you see the LPU. It's a 14 nanometer chip, pretty scrappy, no HBM, so no DRAM on the sides, no silicon interposer, probably cost about 1/20th of the chip on the left. So it's very affordable. And it's very regular in nature. So you kind of see almost something that looks like a single core. And the lines that are kind of showing up is showing like roughly how the data moves in a very predictable manner on it. So Andrew's team can reason exactly where the data is on the chip at any point in time. So at every nanosecond, Andrew's team can say, this is exactly what functional units are active. These are the memories that are being accessed. And this is how the chip is working. So that not only kind of enables some superpowers on the hardware side, but it actually makes the software problem significantly easier. And I'll pass it on to Andrew maybe to kind of talk to that piece.
Yeah, 100%. Like ultimately, because we have 100% transparency into every single component in the hardware, oddly enough, it actually makes the scheduling problem easier. And that's not true with, these traditional architectures. Like you don't really know how the cache is going to behave. There's branch predictors, things like that. We have none of that. No reactive components. Like it's 100% controlled by the software. The knock-on effect of that, and I don't know, Igor, if you'll have a picture of this, but effectively we can now scale up the problem. So here Igor's showing one chip, but we can actually now combine these chips together like Lego blocks and use the compiler to schedule that larger problem onto multiple chips. And that is how we're actually getting the extreme performance that you're seeing out of the device. This is very hard to do on multi-core CPUs and graphics cards because you don't really know when chip A is done versus chip B. And again, it goes back, you have to be overly conservative. You have to deal with this dynamic routing between the chips. We have none of that. So we're kind of treating all these chips as one monolith substrate that we schedule onto. And then that's how we get the sort of blazing performance out of the device because they're all working as one.
There seems to be two principles which I try to live by that have shown to be true here as well. Number one, simplicity typically wins, right? The less complexities you have, the easier it is to reason about, and thus you could eke out a lot of performance benefits. And number two, innovation oftentimes comes from constraints. So the fact that you weren't a huge team, the fact that you didn't have unlimited funding to hire thousands of engineers forced you to think about the problem in a different way, and thus this innovation came to be. So I love it. I absolutely love it.
Yeah, and the big companies are being totally rational in how they approach the problem, right? Like they've invested so much in their kernel libraries, they invested so much in the existing silicon. What is the rational thing to do at that point? Well, you incrementally update based on your existing worldview. You incrementally update that architecture to be a bit faster for, let's say linear algebra, because that's so pervasive with machine learning. And so what are you going to do? You'll maybe widen the vector lengths, you'll add a few more compute units, but the architecture itself is still at the end of the day a graphics card or a CPU. Like you're still kind of in that domain. And then like Igor said, like we kind of had the luxury of just starting from scratch. It's like, really, what would you actually build if you're solving this problem? Like, you don't have the inertia or legacy decisions that you're tied to. You're essentially able to sort of start from scratch, and that's really enabled us to get out of that local minimum that so many of the other companies are stuck in.
Yeah, and the inertia is kind of the key piece, right?
Yeah.
Once you invest into armies of kernel writers, are you going to start from scratch and open up a brand new architecture and do the investment, the software investment again? Or are you just going to keep marching forward and trying to squeeze out any little bit of Moore's law that's left, any bit of network performance that's kind of left. I think that's the challenge. And I think the simplicity, Matthew, as you touched on it, not only starts at the chip level, which we showed, but now we move to the network level. So at the network level, we have taken what is a conventional network on the left, which could has like three strata where you have compute, which, as we described earlier, is non-deterministic. That's basically being kind of routed or switched with networking, which is also non-deterministic, right? The network is kind of trying to manage these packets that are moving from processor to processor. And they're trying to make locally optimal decisions. They're not optimizing the overall problem. They're just trying to minimize congestion in a specific.
And Igor, if I can interrupt for a second, let's take just a quick step up from here. When you're talking about a network, when you're describing a network, what do you mean exactly?
Yeah, so what I mean is that you have these processors that are executing some portion of the task. AI is no longer a single chip problem. AI needs to be tackled by hundreds, in some cases, hundreds of thousands of chips that are basically all working together on a common problem. Okay. So in order for us to do this, you need to connect these chips. They need to communicate with each other. And that is the network. And then network is usually plagued with routing challenges. How do you make sure that chip A talks to chip B, and at the same time, chip C talks to chip X, for example? So there's collisions that are taking place in these switches and routers. The routers are trying to decide who gets prioritized. How do they maximize the bandwidth from one processor to another processor? And that usually results in a high latency, but also non-deterministic latency. Again, that packet might arrive fast or it might take longer. And now software is left with the really difficult task of trying to schedule a really well-behaved algorithm, like a data flow algorithm, into non-deterministic mess of hardware underneath it. And this is where you see these large number of kernel writers and PhDs that are trying to optimize how those kernels are kind of designed.
Got it. So it's not only that the chips themselves are non-deterministic, but then when you put them in, layman's terms, basically a big server room to talk to each other, then all of a sudden there's additional complexities because each one is essentially operating independently, non-deterministically, and you have to write software to account for all of those complexities, and all of that additional software also causes latency. Is that all correct, what I'm saying?
That's exactly right. And when you have a variation, what do? You bound it at every level. And every time you bound it, you accumulate that margin at every single spot in order to be able to kind of execute a specific workload.
Very cool. I just love the fact that all of this came from the fact that you just didn't have enough money to hire a bunch of engineers. Like I love that. That is how innovation is born. Very, very cool. Okay, so then like switching over to how Groq operates, what does that look like?
So what we've done is we have totally removed this networking layer. So what we've done, our chips are not only an accelerator, an AI accelerator, but they also are a switch in one. So we do not have top of rack switches. So we don't have these very complex, expensive BOMs for building systems. Our chips simply talk to our own chips, basically. And they're really tightly connected in these global groups. And then they're also connected to other local groups from each of these chips. So if, for example, if this chips want to talk to this chip, for example, you might have to do a local jump, then you got a global jump, and then you go back to the local jump. But the beauty of this is not that we have less hops that we need to go through, which automatically improves latency, improves the bandwidth between chips. The beauty is that software gets to orchestrate this whole system because even the system level is also deterministic. So we have actually created almost like a mega chip made up of many small chips in a big system. And now the software gets to schedule not only how the compute is being executed inside one of our chips, but also how the communication gets executed throughout the chip. And Andrew can probably add a lot more there than I can.
Yeah, and Andrew, I have a question for you. As you're describing what Igor is talking about, I'm guessing there's been a ton of software written for the conventional type of network, and so now you don't need that. And now, there's a ton of software written for the traditional GPU. Did you have to build all new tooling, even though it's very simple? Did you have to build new tooling for yourselves? What did that process look like?
Yeah, 100%. This is a very different software stack. The problems are different. The approaches are different. I mean, we're still using some common compiler infrastructure out there. At the end of the day, you don't want to sort of rebuild everything from scratch, but ultimately the approach is very unique to our silicon. So it goes hand in hand. It's like a entire platform. You can't just have the silicon on its own. It's sort of bolted with the compiler and how the compiler maps these machine learning workloads onto both the silicon and its ability to do this, as it's shown here, the software schedule direct network. So the software is sort of orchestrating everything. You kind of think of it, and this is where that determinism point comes into play. If you know exactly how long every single chip is going to take to run, some basic block XYZ, you know exactly when to send things over those lines. Like the problem becomes actually quite tractable at that point. And if you don't know, yeah, as Igor says, you have to sort of bound it and be extremely conservative. Yeah, I really like this picture that you're showing here, Igor. I don't know if you can explain it.
Yeah, so I mean, I was just trying to help with your explanation, but if everything is pre-scheduled, Matthew, and you know exactly the latency that's traveling, it's almost similar to you taking your car to work in the morning and somebody telling you, Matthew, leave at 8 a.m. exactly, drive at 40 miles an hour, don't stop at intersections, don't stop at stop signs, just keep driving along this route, and you're going to get to work at exactly 8:23 a.m., for example. And this is how our network works, right? Everything is pre-scheduled. Each of these cars could be a tensor that's being sent through the network. The beauty of it is not only can you make sure that these tensors get to the location fast because everything is pre-scheduled, but you can actually get more utilization out of your roads, which are chip-to-chip connections. These are the wires that are connecting chips together, right? So we can schedule because nobody has to stop. There is no traffic jam. So you can actually move this really quickly, right? And on the left, you see the conventional network, which typically, if there's a congestion, there needs to be a whole bunch of decisions made. Back pressure on the kind of link that's coming in. So you're telling him, hey, you got to slow down with your packets or try to figure out a different adaptive route to get to your destination. Ours is orchestrated on the right. On the left is kind of like making a decision on the spot, kind of like you're trying to kind of make decisions. So I think this is kind of along the explanation that Andrew kind of gave. Yeah.
Yeah. Yeah. And to your point, Matthew, about how did you think about the problems? Like, it's so different than your traditional architectures. It's kind of funny you mentioned that because we did have some folks who were experts within CPUs. They spent years at these big semiconductor companies, very successful, by the way, building, CPU compilers or, solving the multi-core problem. And some of them actually struggled looking at this because they kept on trying to map the complexity of that world into this world. And it just there was friction there. It just didn't work. And they really had to forget everything they learned and start from scratch. It's a totally new framework in how you think about these problems and how you map these sort of HPC and ML workloads onto silicon. It kind of flips things on its head, which is interesting.
So I want to talk for a minute about use cases. So completely different and unique architecture obviously has applied extremely well to inference. Are there other use cases developers or anybody should be thinking about with regards to how the Groq chip works? And are you planning on expanding the applicable use cases in the future? Anything you can share would be great.
I mean, it's interesting. Inference is by itself a pretty broad category. But yeah, definitely beyond LLMs, we have definitely seen very specific use cases where the Groq architecture shines. And it comes down to the fact that it wasn't obvious from the images, but internally, there's actually a ton of memory bandwidth on the chip. So why does memory bandwidth matter? Well, you got to feed the beast. So you have to be able to suck in data and feed the compute units on the device as fast as possible. Otherwise, they often call it starving for data. Otherwise you're kind of just sitting there doing nothing, just waiting for your data to come in. Because we have that superpower within the hardware, there are a ton of different areas, and Igor's listing a few here related to drug discovery, things where there's a lot of recurrence in the application. So, there's other types of deep learning models like LSTMs, RNNs, graph neural networks. We actually shine extremely well for all of those things as well, on top of the LLMs that the LPU was designed for. So it's this really nice superset of problems that we can tackle because the architecture is so different, and we can take advantage of those characteristics that are unique to us.
This may be a naive question or just a lack of knowledge. Would we ever find a Groq chip in consumer hardware?
The architecture is very organized and very regular. So if you look at the chip, the vertical lines effectively on this chip are effectively SIMD structures. So these are structures that you can feed specific information, and you provide an instruction from the bottom of them. So they're kind of replicated, so you can just tile them right next to each other to build the chip. So we can very quickly tile a version of this chip that is something that can be embedded on a piece of other silicon. It could be taped out as a chiplet, or it could be a kind of a chip, a standalone chip that we have kind of shown up to this point.
Got it. So, one thing I'm particularly excited about in the future is being able to run really powerful large language models locally, and especially on, maybe even my phone or other devices that are mobile. Is that potentially something I can look forward to with Groq powering it?
I think the beauty of Groq is that the latency is so low, Andrew, that you can actually run that. You can run large language models on your cell phone right now, right? So I don't know if we want to do this on the spot here, but we can try something. Let's see how this is going to work out. Let me know what question you wanted to ask, for example. Do you have a question?
No, go for it, Igor. Go for it.
Okay. Can you tell me more about artificial intelligence hardware and the biggest challenges for it?
Sure. In the context of artificial intelligence hardware, some of the biggest challenges include power efficiency, scalability, and computational capabilities.
Yeah, so that's crazy because it's very low latency, but you're still hitting a server. Is there a world in which it can be completely local, the actual models running on device?
Yeah, so the question, and Andrew probably can talk to this more intelligently than I can, but typically with the larger number of parameters, you get better quality of the model. Technically, we can map smaller models into our hardware, or maybe a version of our hardware with maybe some DRAM on the side, but those are the trade-offs. So as I mentioned, these are multi-chip problems at this point. Even if you're using GPUs, you still need multi-chips to tackle the biggest large language models. So it becomes a quality versus size kind of trade-off. But as we move in the future and we're trying to do more and more integration and 3D stacking, yeah, perhaps we can get there.
Yeah. The way I look at it is like, you would not have the biggest and baddest LLM running on your phone. Like you wouldn't have like this sort of GPT-4 or, Llama 3 that's coming out soon on your phone. You'd probably have a distilled version of it and potentially tuned for a very specific area. So it'll be much smaller, but you'll be fine-tuned for like, getting your groceries or something. It'll be super, and that'll be the one model that'll run locally, and you wouldn't need sort of the offload if that becomes pervasive. That's the way I would look at it. There'll be kind of these subclasses of smaller models that are much cheaper to run, but probably derived from the massive server scale models that are running, within the large companies today.
So I have a selfish question now. You currently with Groq's API and Groq Chat support Llama, the Llama 270B, as well as Mixtral, the two best open source models out there. Are you planning on expanding that list? What does the process look like to bring a new model to Groq's architecture? And when can we expect another model?
I mean, good question. Yeah. So, I mean, ultimately, the answer is yes, right? Like the technology and software that we built is not like, Llama 2 specific or anything like that. So as the models evolve, we do digest them through the compiler. Like ultimately what we often have to do is we'll take the PyTorch model. There is some massaging, quite frankly, because sometimes they're specially tuned for like, they'll have like Intel primitives in there or some other company's primitives. And we have to sort of make them agnostic to the vendor. And then from that, then we can suck it into the compiler and then we just map it on, we'll run it. And we do this often for some of our internal customers where they have proprietary models and they want to see how well it runs. And we'll do that for them so they can benchmark. So that's kind of roughly the process where we'll take those customer models or open source models, kind of massage the front end of the description to be a bit more agnostic to a vendor, and then push it through our proprietary software stack and run it. And that's about it.
Got it. Very cool. Okay. So two last things I want to talk about. First, I want to talk about the manufacturing. I know nothing about silicon manufacturing. Maybe you can just briefly describe what the traditional silicon manufacturing process looks like and then how it might differ with Groq. And you also mentioned it's all done in the US, which is awesome. So we'd love to hear about what that process is.
So this is probably the most advanced technology humanity has ever built, especially if you combine artificial intelligence with like actual semiconductors. Like I mentioned, we're like putting thousands of transistors in the same size of a single red blood cell, right? Like that's how tiny these things are. They're effectively switches, on and off switches. And they've gotten to the point where they're so complex to make that even the printing initially was done with really just light shining through a mask that would be projected on a piece of silicon that had photoresist, and then you would etch away different features until you got exactly the features that you wanted on the chip. And you would have many of those layers, close to, 70 or more layers in an advanced chip right now that were all printed like that, one after another. Now, this has gotten so complex that normal light is no longer, the wavelength of the normal light is too big for the feature size that you're trying to print.
That's crazy.
So now we've gone to extreme ultraviolet. And on top of that, we're doing double patterning, which means that we're only printing where the waves superimpose to actually create the tiny feature sizes that are found on the latest and greatest chips, right? So this is why this has been such a big challenge for companies like Intel and Samsung to catch up to TSMC. TSMC has been kind of leading the pack here, but we're seeing more and more investment into it. We saw Sam Altman asking for $7 trillion to kind of build his own fab. As Jonathan puts it, I think if you have a clever architecture like ours, you should be able to do it in 1/100th of that kind of investment. But this is a really complex technology, and you can see it. It's kind of at the forefront of all the geopolitical discussions that we're having at this point. Yeah. But hopefully that gives you a little bit.
Absolutely. And then, like, are there specific qualities about the Groq chip that made the manufacturing process different? Or did you have to invent something? Because you talked about using ultraviolet. Is that unique to Groq, or is that unique to kind of the more modern chipset? And what is unique to Groq specifically?
Yeah, so I think we have followed the normal logic process that is part of the fab. So we haven't had to modify anything in the fab. The one thing that's really nice about the Groq chip is the regular nature of it. So because you can see it really looks very much you can see just different shapes that are kind of replicated from left to right. And regularity is kind of critical. As soon as you push the limits of the process deeper and deeper, more regular structures will scale a little bit better, especially, right? Or you can be able to squeeze a lot more transistors in an area if it's very regularly behaving. Like an SRAM will have a higher transistor density than just a normal logic block that would have, because everything is regular and perfectly organized. The beauty of Groq's chip also is that we do not have a lot of control logic on the chip. So the instruction portion, the instruction controls of the chip only make up about 3% of the die. So the rest of it is devoted to really what matters, compute and memory on the chip. In a typical GPU or a CPU, you will see the control logic taking upwards of 20, 30% of the silicon area. So that's really just trying to kind of introduce these dynamic decisions the hardware is making on the chips. You need a lot more control, a lot more networking on chip, and so on. So we've just replaced that with the transistor that actually do the work rather than kind of control the rest of the chip.
All right, that's helpful. Thank you. I want to switch gears now completely. So I think just a few months ago, most people probably hadn't heard of Groq. And then all of a sudden, Groq is everywhere. So I want to ask two things. One, what was the energy like? And I guess still to this day, what is it like? And then what do you think clicked for people? What do you think was that moment, that inflection point where the broader engineering base, developers kind of realized Groq really has something special with their insane inference speed and the different use cases that unlocks? So what was the change like in energy inside the company? And then what was that moment that you think people really started to notice how valuable Groq's inference speed can be?
Yeah, I mean, in a lot of ways, it feels a little surreal, right? You've been working on this problem for so long. And quite frankly, to give him credit, like Jonathan Ross saw this day coming since the beginning, and people just kind of, they're like, oh, yeah, that's interesting. we'll keep on doing it. But, he was right? He might have been a little bit early in his prediction, but he knew in his core that this architecture, because of how he thought of it, would achieve this level of performance. And the team is extremely proud in being able to see this happen. And internally, it's kind of funny. Like when you're working in the space, you don't really realize what has changed. You're kind of like day to day, you're doing the same thing over and over again, just making things a little bit better each day. And then I think it's really that push, like Mark Heaps, Jonathan, they make it real. Show the world that this is not just an idea. Make this thing real and accessible to everybody. And that's really the decision that we made, roughly late 2022, early 2023, that led to this moment, ultimately. Like just sharing the technology. I mean, there's a lot of engineers within Groq, and we were like, no, this is way too early. We're not ready. But we kind of got a little bit of kick in the bum and just pushed it out there. So it's been super exciting.
Yeah, so Groq is one of those 8-year overnight success stories.
Exactly.
That, people see it and they say, wow, came out of nowhere. But no, you guys have been grinding for a long time. And then was there a particular marketing event? Was there some kind of, how long has Groq Chat been up and functional? And then when did people start realizing, and when did it really go viral, I guess is the right word?
I mean, I think October 5th of last year, right? Roughly.
Yeah, I believe so. Yeah, I think it was Llama 2 that kind of showcased the capability that we had on the hardware. So we had the capability, we have kind of used it on a number of workloads successfully, but I think it was kind of Meta going open source on the large language models that kind of gave us the ability to showcase the capability of this hardware. And I think, as Andrew pointed out, I think that was kind of like the tipping point on our side. Yeah.
Yeah.
And since then, it's been hard to go to sleep. Yeah.
So I'm particularly excited about taking the inference speed and plugging it into AI agent frameworks. That is just one area that I'm really, really excited about. That and coding use cases. Are there any use cases that you guys are particularly excited about that get unlocked because of this inference speed?
So this is a little bit non-intuitive, but the behavior of the model, because we have such fast inference speed, actually lends itself to better output. And so what do I mean by that? So there's this notion of conscious of thought, right? You basically get higher quality answers if you stream in successive answers back in and rephrase the question It's almost like you're teaching the model on the fly. You're kind of giving it more information. I think that is really unlocked with the Groq architecture. Like, you're going to see these models supercharged now. You know, there's going to be less hallucinations. There's just going to be higher quality answers because you have faster inference. This is something that's non-intuitive because people generally just think, oh, I'll get my result faster. No, you're going to get a better answer. So that's the thing that excites me.
Yeah, that is so cool. I don't think I thought about that specifically. I mean, it's kind of adjacent to AI agents, right? Because if they're working together, if they're checking each other's work, it's kind of the same thing. But are you describing an LLM can actually run or provide multiple outputs, iterate on those outputs before it even presents you with the final output?
100%. That's exactly it.
I didn't even consider that. That is so cool. So have you implemented that with the models that are live on Groq Chat today?
I mean, we have some POCs with some of that, but no, we haven't exposed anything at a commercial scale yet.
But anybody can try that, Matthew. Maybe you can play with any of the large language models and keep feeding your information, asking for better suggestions, and then implementing those suggestions for an answer and kind of try to see if your answer is better, right?
Very cool. I have so much building ahead of me. All right, I know we're over time. I want to thank you, Andrew, Igor. This has been so fascinating. I'll probably have other questions. I know a lot of the viewers who watch this will have a ton of questions as well. Maybe I'll send some follow-up questions. But I appreciate your time so much. This has been awesome.
Awesome.
Thanks,
Very
Matthew.
nice.
All right, we'll talk soon.